Quick introduction to myself. I'm Brandon Chavez. I'm a solutions architect, and I work with the Amazon Partner Network. So I work with technology partners and help them build solutions that work well with the AWS platform. And so specifically, I work with the Amazon ECS and like Docker community. So building a community, an ecosystem around ECS, and really helping to build products that augment and enhance the AWS offerings. So today's a deep dive. And we're going to talk about microservices and how they apply to containers, how you can build microservices with containers. But we're not going to jump right into the really heavy stuff. There will be a little bit of an introduction for those of you who are unfamiliar with either the architectural style or with containers or with ECS. So maybe about the first 15, 20 minutes, we'll talk about that stuff, make sure everyone's on the same page, introduce some concepts, and we'll go from there. And then for Q&A at the end, I'm actually really excited to mention that we have some members of some partner solutions. So we have Datadog and we have Shippable here, and we'll all be hanging out up front for like 15, 20 minutes afterwards, and we'll answer questions and talk about how all of that works together. So let's go ahead and get started. So the first thing we're going to do is we're going to introduce the concept of microservices, so what they are, what are the benefits of this approach, and how they really differ from other architectures. I also think it's relevant to note that even if you aren't building microservices with containers, a lot of the design principles we'll talk about are kind of broadly applicable to cloud architecture in general, because things like scalable and decoupled architectures are really kind of critical to any successful cloud architecture. So like I said, we'll start very broadly, we'll define this pattern, and we'll rapidly get into implementation specifics and then culminate with a demo of some of this stuff working live. So number one, what are microservices? And here we have a quote from Wikipedia, which is a little bit silly initially, but it's actually interesting to me to find out that this is like relatively static, which means that we have some sort of agreement from the community on what this architectural pattern or the approach actually looks like. So at a high level, what do we have? We have your application composed of a number of small services, and each service is backed by its own processes that are usually abstracted away behind like a well-defined interface. And so today we usually see that as like an HTTP endpoint, like an HTTP RESTful API. And generally each microservice is built around a single business function or performs a very specific task very well. So how does that compare to other major architectural patterns? Monolithic is probably the most clear-cut. Probably everyone in this room has had experience with that sort of application. Everything in that application is really tightly coupled. So if you change functionality in one part of the application, you probably need to test functionality of the entire application after that, right? So all the components are likely to depend on the same backend, for example. They might share the same memory. Tight coupling is really what we think about when we talk about monolithic applications. And then the next step towards microservices is really a service-oriented architecture approach. And so this is breaking out your monolithic application into a couple of different domains. But that business logic might still span several of those domains. And for me, it's really common to associate service-oriented architecture with some form of middleware, like an enterprise service bus that does tight coupling of a couple of those different components. So still, a change in one part of your application probably triggers testing across multiple parts of the application can be a very time-consuming process. And then finally, when we get to microservices, this is composed of, as the name implies, very many small services, very many small components. And each component exposes an API that really abstracts whatever language or data store is behind that endpoint. So the business logic tends to live inside one domain. And if you make a change to a service, as long as you don't break functionality on your API, the tests just need to really verify the functionality of that one service, right? So you can make changes with a little less concern for breaking the entire application, less unforeseen consequences, ideally. So why would we want to move away from monolithic architectures in the first place? What are some challenges you might have with this approach? So I think the main challenge is giving any of the subcomponents a degree of autonomy here. And that could include maybe limiting developing teams or development teams from moving at their own pace, right? Developing new features as they see fit. They might have to wait for other teams. It might be impossible to change one component without changing another component. And then also scaling. So you cannot scale individual components. It becomes very difficult to do so. So one part of the application might have very intense CPU requirements. One might be memory intensive. But you cannot break those out into appropriate fleets underneath. So to scale, basically you have to replicate the entire thing across many instances, generally the same instance type. And this really limits your flexibility and it makes it really challenging to have efficient resource utilization. So you can approach these problems a little bit differently with microservices. These loosely coupled components, they can be placed in their own set of underlying instances. So when you scale out each component, you can do so individually. And this pattern is really natural for the cloud. I'm sure you can start thinking about how this would work, right? You can have different auto-scaling groups, different instance types, different launch configurations for each service. You can scale them individually based on metrics that make sense for each of those services. And here in this example, the user service, for example, might be the most heavily trafficked service in your application, and you really only have to scale that, whereas the shipping service, for example, might be relatively low traffic, and you don't really have to scale it too much. It can be a single instance, 2 instances, something like that. So it really helps you track your resource utilization in a way that makes more sense instead of just replicating the entire application across your fleet. So if I have to summarize these characteristics of microservices, a core tenet is really the fact that no matter the language or the data store or the back-end workflow that your microservice uses to do a thing, it's really just exposing a consistent API for other services or maybe your users to consume. And so this API that you're exposing is really, it's a contract, right? And so you're prioritizing that you're maintaining that functionality, that API at all costs. As long as you're doing that, this really frees you up and it turns your service into a black box. So maybe as a developer of this service, I can write it in Python, I can write it in Go, I can write it in Node. No one really cares because at the end of the day, it speaks HTTP, and that's great. And that's great for the consumers of that service too. So if I'm a user or a consumer service, I don't really have to worry so much about how it works behind the scenes. I have to really understand how that API works and how I'm going to interface with it. But as long as I can rely on that API remaining fairly consistent, then I can build my service against that API and consume functionality from that service without having to know too much about how it works. So high-level summary, it sounds great, but of course there's challenges with any different approach that you might take. And some of these are not really microservices exclusive problems. So with cloud architecture in general, there can be increased deployment and operational complexity when your scale gets huge. You can have many distributed services. Each one can provide different functionalities, so you have to keep track of all of that. And so I think it's important to kind of work through some of these challenges. These are things that customers generally come to us with challenges, and they want to understand how to resolve them before they actually go to production with a microservice solution, especially on ECS. So let's try to address all of them one by one. Number one is resource and state management. And I think this is probably more broadly known as orchestration. It's a very common term to describe this problem right now, or a approach to this. So basically what it means to me is, how do I know what resources I have available? And what state are they in? And how do I make sure that's all kind of configured how I want it, right? There's a lot of distributed things, a lot of stuff that I have to control. How do I do so easily? And so we built EC2 Container Service for running containers at scale across clusters of EC2 instances. So why is ECS the right thing to talk about when addressing resource and state management concerns in microservices architectures? Let's talk about that. And so I think the reason that containers and Docker are so natural for the microservices pattern, there's a few reasons, right? Number one is it makes services really simple to model. And that's because the application and all of its dependencies are all wrapped together into a redeployable and immutable image, right? So that's your Docker container. Inside that container can be any app, any language. That's that black box component. And the image itself is a versioned artifact, so it can be stored in your repository or a repository like your source code is. It makes it easy to kind of understand, which revision might track to which revision of my code. And that simplifies deployment. And I think another reason it simplifies deployment is because containers kind of enforce a stateless service model. So when you encourage a stateless service, it kind of decreases the risk of change because each deployment can just be a new set of containers. For the same reason, you can kind of roll back very simply with little challenges. So I think it just makes it more straightforward to decompose your applications into microservices by using containers. And it's just because that microservice is self-contained in a container, and it allows you to reduce dependency conflicts and ultimately decouple deployments. So a couple of years ago, when Docker was still very new, we talked to a lot of customers and realized that while it's pretty easy to manage a handful of containers on 1 or 2 hosts with just the Docker utilities, when you take these applications and run them at scale across a large number of hosts, it does become more of a challenge. And to kind of support that notion, to kind of quantify that it's difficult, I guess we should ponder a few questions. So if I have hundreds of containers, dozens of hosts, they're spread across availability zones, how do I keep track of which hosts here are actually available, right? How do I hook my application up to elastic load balancers? How do I know how much CPU and memory is available on that host way up in the corner, right? How do I know if one of the containers dies on one of the hosts down here in the bottom right corner, right? There's a lot of things to keep track of. And so what if I want to do deployments across a fleet of this size? And so these are questions we had from customers, and this is the reason we built ECS, and we think it's a good solution to a lot of these problems. So real quick, now we're going to touch on a few components of ECS, kind of how it works, before we start diving into some more of the specifics of actual implementation details. So ECS was really built to let you make containers a foundational building block of your applications. And we want to make them first-class citizens in AWS. So the idea is to give them full functionality equivalent to EC2 instances eventually. But right now, ECS really eliminates the need for you to run and manage a cluster manager or a state management system for your cluster. So we have a state management system that we've built. It's based on top of some primitives we've developed internally for managing very large clusters. And all of that is exposed through an API. And that API is really intended to give you full visibility and control over all the resources that are in a cluster. And so this API is really scalable, and it can support clusters of nearly any size. And this is a load test that we ran over 72 hours, where we ran list and describe APIs basically continuously. And we adjusted the size of the cluster up to over 1,000 instances. And really what this is showing is that we can provide really detailed state tracking, even if your cluster is very large or dynamically changing. And so the red and green lines show P99 and P50 latencies. And the purple line is instances. So I think what's really important here is to note that it's relatively stable, it's predictable, and no matter what size your cluster is running, you should be able to expect ECS to respond in basically the same way, which is very important. We've also built schedulers. So there's a scheduler, actually a couple of schedulers that are operating on the information that that backend state management engine provides you. So that means we can find a place to run a container based on the requirements you've specified, right? So the schedulers operate on the information from that backend state engine. They know what's available around the cluster. They can look at the job you've submitted. They can say, this is how much memory or CPU I need, and we can throw it at the cluster and run it in an optimal place. A cool thing to note is that these schedulers operate on the same APIs that we expose to you, the same information that's exposed through the backend APIs. So in theory, or actually in practice when we've seen this, customers can write custom schedulers based on the list and describe APIs, and they can take information about what's going on in the cluster, make educated decisions about where should I actually place my containers based on some certain application or business logic. Also, ECS is really built to work with the AWS services that you already use. So you can throw your cluster into a VPC, for example. You can use security groups to control access to the EC2 instances in the cluster. You can store persistent information on EBS. You can route traffic to your containers using an ELB. Chances are, if you're using something in AWS already, ECS has you covered, and you can use that functionality with ECS. And then real quickly, let's touch on some of the constructs within ECS, so some of the components. Number one is a cluster, right? So this is a collection of resources. It can span availability zones. It's constrained to a single region, but it's a dynamically sizable namespace consisting of EC2 instances that are basically aggregated into a single resource pool. So all of the memory and CPU is aggregated and presented to you as available through the APIs. We often see customers using different clusters for different components of the same application if those different components have different scaling requirements, different security requirements, or if it's just easier for you to process this particular component lives on this cluster, this particular component lives over here. And it's also common to use them for different environments too. So if you have a development environment, you might use a cluster for that. You'll have a test cluster, a production cluster, so on. It's really nice for a logical placement boundary of your containers, and it's a very easy concept to understand when you're actually using it in practice. Next are tasks, and tasks are the primary unit of work in ECS. And so a task definition is a JSON document that defines which containers should be deployed together onto the same host and how they should be configured. So you can have multiple instantiations of the same task running across the cluster. you can have a number of different tasks with their own unique container definitions running on any given cluster. So a task is just a way of deploying the containers that you want to run together. If your application requires a couple of containers to always be on the same host and have that communication, then a task definition is very intuitive. You can also have a task definition with a single container, and that's a very common approach, and that's what we'll be showing later on. Services are a higher level construct than a task, and so a service allows you to define how many of a specific task should be running on any given instance, across the cluster, actually. So we have an API for creating and interacting with services. You can tell it, I need 5 tasks running continuously, and the service scheduler will find a place on the cluster to keep all of those running. So services, there's an API for interacting with them. We also have a service scheduler, which handles the logic and is what's actually doing the work when you make the API call to the service API. But we'll talk about that more. I guess some other cool stuff about services, like I said, it will find a place to put all the tasks that you want to keep running on your cluster. It will replace failed tasks. It finds places to run new tasks. It can help you hook into an elastic load balancer. Very useful construct in ECS. So the next challenge is monitoring, and I think that everyone really loves monitoring. It's always hugely important, especially if your infrastructure is very dynamic, and that is no different with microservices. So what are the approaches you can possibly take to handle this? And number one is ECS provides some default CloudWatch metrics that provide metrics for both your clusters and your services. And so we provide both cluster level aggregate metrics, and that means across the underlying instances in the cluster, and then service level aggregate metrics, which means across the tasks running in a service. And then we also provide both reservation, so that's how much memory is reserved for a container to use, and then utilization, which is how much it's currently consuming. And so these are visible through the console, through the standard CloudWatch graphs. But I think one thing to clarify on is utilization versus reservation, because I usually get a lot of questions about that. So when you run a container, you specify how much memory is reserved for it. So if you have 3 containers and you've said that each one of them need 100 megabytes, you would have 300 megabytes of reservation across your cluster. However, each one might only be using 20% of the memory at any given time, so that's current utilization. And these are both useful for kind of understanding like how much is placed across your cluster and what is your current utilization. They give you different ways of basically alerting on what kind of utilization you have across your cluster. And this is not unique to ECS or containers, but I think it's awesome with CloudWatch. You can monitor additional metrics, such as something like disk space, which we don't tell you by default, using the CloudWatch monitoring scripts. And so you could run this on each container instance in your cluster, for example. CloudWatch is pretty cool. But I'd also like to start introducing some cool stuff in the partner ecosystem. And Datadog is one of our favorite monitoring solutions out there because it's really purpose-built to monitor highly dynamic infrastructure, and that includes containers. So the granularity of monitoring provided by Datadog, I think, is really impressive. Some of the stuff that I like, first of all, is they have official ECS integrations. So what that means is they have documentation and guidance on how you actually use Datadog with ECS, which is very helpful. But they also provide like a lot of custom ECS metrics, like how many tasks are running, how many are pending. They track task and container life cycles. It's also cool that when ECS brings new containers online, Datadog automatically can begin tracking those metrics, and it can take note of what's running inside of those containers as well. So Docker metrics can be viewed individually in dynamic groups, or they can be correlated with metrics from like the rest of your infrastructure. So a bunch of different views on what's actually going on. And as I mentioned before, Datadog is here with us, and we can talk to them after in the Q&A session. Another good monitoring option that we really enjoy is Sysdig Cloud. And they're able to extract metadata from Docker and ECS. And they can, from that metadata, then like infer the logical structure of what your microservices application looks like. So this information is then combined with what they call container vision technology. And that really makes them able to inspect applications running inside containers without any additional agents or anything running inside the container. So it can also give you the ability to view like a historical replay of your container's life cycles, which is very handy for troubleshooting. And I think just in general, you really get like a nice degree of visibility from both an infrastructure and an application standpoint. So you can visualize that logical topology of your application, or you can show the physical hierarchy, the grouping of containers into tasks and services, so on. So Sysdig, another favorite of ours for monitoring and troubleshooting. Let's talk about service discovery. This is where it gets quite interesting, I think. This is a key component of most distributed systems and service-oriented architectures. So back before cloud computing, it was much more acceptable to have statically addressed resources. So you probably knew where your database server was, maybe physically. It had an IP address that was static. It had a reservation in your DNS system. If any of that changed, you probably had a problem. You might be picking up the phone to call somebody and yell at them a little bit. However, now we kind of accept that as a change or as a constant, right? So change is a constant. Cloud architecture is highly dynamic, and this is especially applicable to containers because they frequently spin up. They live on a certain host with a certain IP and a port, and they live for a short amount of time. And then they might get spun down and then launched on another host with a different IP and a different port. And you have to somehow cope with that. Your application has to somehow be okay with this dynamic rate of change. So how can we make our applications okay with this? And one option is you can abstract these dynamic changes behind a relatively static endpoint by using an elastic load balancer and a CNAME. In this case, you'd probably use a single elastic load balancer per service. But you can, of course, use ELBs in a private subnet, right? So if you want them to front back-end only services. But in this case, we'd recommend using a Route 53 private hosted zone, so those CNAMEs that are mapped to your ELBs are only resolvable from within your VPC. The thing about the ELB approach, though, is it's not necessarily the most dynamic because if you're using this approach, you're probably still hard-coding some CNAMEs into your application somewhere. And if you get to a point where you've exceeded a couple of ELBs, enough to fit on a Post-it note, you might start considering something more purpose-built for container service discovery. And so one option that we like a lot is Weave. It's super intuitive, and it provides a DNS interface for cross-host container communication. And I think a quick summary of how this works is it allows you to reference containers by their name, like you would locally with Docker links across the entire cluster, and that's basically it. So a very easy concept to understand. It's very transparent in practice. A little bit difficult to demo because of that, but it's a great solution, and we have a lot of customers that are enjoying using this. So how it actually works, it's made up of a few different components that all run as containers across your cluster. One is the Weave proxy, which sits between the ECS agent and the Docker daemon, and that intercepts communication between the two. So the proxy automatically attaches containers to the Weave network, and it assigns them an IP and a net mask and all that cool information when they're started up. And then another component is WeaveNet, which implements an overlay network between Docker hosts across the cluster. And then it uses a gossip protocol to share topology information across the cluster. So a really cool thing about Weave, even though it's an overlay network, is that it's actually very, very fast, very low latency, because it allows the packets from your application to go directly to the kernel instead of through another container in user space. The WeaveNet router basically shares information with the Linux kernel's Open vSwitch module and tells it how to process packets. So the application that you're running in a container can just make calls directly to the kernel, and it doesn't have to route requests through another container, adding more latency. So that's really awesome. And we'll demo Weave at the end as well. So another option is sometimes you might want a key value store. Sometimes that's the right option if you have more configuration data you want to provide to your services. And this is really the principle that Consul by HashiCorp is built upon. And we actually implemented this in our reInvent bootcamp last year. Very, very popular. It works well. There's kind of a lot of things going on, a lot of different components that make it truly dynamic. So we'll look at the architecture in just a second. But a quick summary of how it works is it basically maintains a cluster of servers and clients that communicate over Surf, which is HashiCorp's own custom Raft implementation. So I'd love to talk about Raft and Surf extensively here, but you guys should go take a look at that on HashiCorp's documentation page because they have like a pretty sweet zombie apocalypse analogy, which I found endlessly amusing. So take a look at that if you want to know more. But essentially, it allows you to correlate information like host names, IPs, ports, and whatever other configuration information you might need to pass to your services running in containers. So looking at the architecture, there's a few moving parts that are required to make this really dynamic. So on each host, you need the Consul server or the client, so the host partakes in the cluster. You can run a collection of 3, 5, or 7 servers. And then you also need something called the registrator container, and that listens for Docker events and then communicates them to the rest of the cluster. It updates that information in the key value store. And then inside your processes, optionally, you can have something called env Consul, which is a wrapper process. It's like a supervisor inside your container. And this is so that if you're monitoring a particular key value pair for your application, something important like where is my database, env Consul can reload the environment variables and then restart the process inside the container instead of having to have the whole container restart to get new configuration information. And then finally, let's talk about deployment. I think deployment really covers a lot of different topics. So this can be things like scheduling. This can be things like continuous integration and continuous deployment. This can be managing build pipelines. There's a lot of different things that go into deployment. And so we have a couple of, like I mentioned, 2 schedulers that we've built that are integrated with ECS. Like I said, you can write more if you want to, if these do not meet your business requirements. But the first one is a batch job scheduler, which is really built to run short tasks. So something you will just throw at the cluster, have that job complete, free up the resources for the next batch job. A really natural fit for containers as well. I don't think I explained this well enough, though. So schedulers work by querying the state manager. And so they identify a place where containers should be placed. By basically comparing the application resource requirements and then the availability across the rest of the cluster. And so our service scheduler, which is for long-running apps, will also take things into consideration like availability requirements, like should this be placed across multiple AZs. It should understand like how containers should be grouped together, should they be distributed, et cetera. And we're continuing to add features and new support to the service scheduler to support new deployment models. And we'll talk about a couple of those here. So some other cool stuff about the service scheduler, it gives you the ability to associate an ELB to your service, which I think is very, very helpful. So when you correlate that ELB to your service and you scale up your service, it will automatically check in new tasks to the ELB, and you don't have to worry about that yourself. So very helpful. It will also try to gracefully drain connections when it's bringing down other tasks in this service. So you can also use all the standard ELB features, so things like health checks and grace periods, and configure your application just like you would if it was running on an EC2 instance behind the ELB, except for in the console, it does look a little bit weird because it doesn't show the instances as being registered with the ELB. That's all handled through the service scheduler, and you'll see that in the ECS console in just a little bit. And so this is a relatively new feature, is the ability to manage deployments with the service scheduler. And so the parameters we introduced to control deployments are minimum healthy %, which represents the minimum number of running tasks during a deployment or an update of that service. And then the maximum %, which represents an upper bound on the total number of running tasks during a deployment. So it really enables you to define like the deployment batch size. So let's visualize that a little bit. It's a kind of a difficult concept in practice or in theory. In practice, not so much. But so here's a more concrete example, right? So it's essentially a rolling deployment. That's the way you should picture it. So basically, make sure my service doesn't grow past its current size during a deployment, and kill at most half of the tasks that are running at any given time in order to roll out a new version of my service. So this, for example, we can kill at most 50%. We'll only drop 2 of them out until 2 new ones come online, and we'll keep 2 of the old running before we bring up 2 of the new ones. So rolling deployments are one option. Another option you can have is basically like a blue-green style deployment, I think is the best way to think about this. And this option here, where the minimum healthy % is 100% and the maximum % is 200%, says add a whole new batch of containers alongside my existing set, and then kill the old set when the new one is actually ready to go and responding to health checks, right? So you might use this option if you can't reduce service capacity during the deployment, or like space in your cluster is not really a concern, where you just want the new ones up and running in the quickest way possible. And then the last way of really doing deployments, I think, is kind of like a classic blue-green deployment. And this is very similar if you've used Elastic Beanstalk or regular load, or just EC2 behind ELBs, basically creating a whole new service with a new task running behind it with its own ELB. And you have to be using a CNAME for this, of course, but basically, you could use Route 53 weighted routing policies and gradually start weighting traffic to the new service. You'd watch for errors or anything like a performance regression, and eventually fully fail traffic over to the new service. And so the other side of deployments, besides worrying about schedulers and how you're actually going to roll things out, is probably managing multiple deployment pipelines. Each microservice will have its own build pipeline. It will have its own test stage, its own production stage. And you have to manage all this, and it becomes very, very tedious to do it your own. If you're in there updating containers yourself and you're editing task definitions to refer to those new containers manually, editing a whole bunch of JSON, and you're doing that multiple times a day, it's going to eat up a lot of cycles. It will really limit your ability to do things in a dynamic manner. So we really support using one of our CIICD partners for deployments. We have a number of good options here. All of these CIICD partners can do deployments directly to ECS, which is really awesome. They can automatically rebuild task definitions based on new versions of your containers. So Circle CI, CloudBees, CodeShip, Shippable, Solano Labs, Worker, all of these support ECS directly, which is great. So for this demo, we're going to focus on one of these, which is Shippable. And let's summarize Shippable real quick. Let's take a look at this architecture. So Shippable, I would summarize as a hosted cloud platform for doing continuous integration and continuous deployment. So that includes things like testing your code that lives in GitHub or Bitbucket, and then creating and running Amazon ECS services and tasks on your ECS clusters from within the Shippable console. So Shippable can keep your Docker images in either Docker Hub or Amazon ECR, which is our own Docker registry. And then it can take those and deploy them into ECS. So this is really great because, as I mentioned, it prevents you from having to do any manual updates of things like task definitions. It will automatically configure your services for you. And it will take that latest image information based on a successful CI build, and then either automatically deploy it or notify you and give you a single-click deploy option, which is great. You can deploy to multiple stages in your build pipeline, so you can have a test cluster and a production cluster, and it's really simple through the UI. So let's get into the demo, the real interesting stuff. So the first part about this demo is that we have a running ECS cluster. It's going to have two services running. One of them is a front-end application. It's written in Flask, so a little Python application. It's basically a hit counter. And the back-end application is a Redis container. It's a Redis service. And so we're just using that to illustrate the communication between the two. Also of note, on this cluster, we have Weave service discovery running, and that's how the containers are actually communicating. They're resolving each other's name through Weave. And so what I'll do is I'll kick off a build by committing some code to a GitHub repository that Shippable is actually watching. And so Shippable will be notified that there's new code in the master branch of my GitHub repository. That code will be brought into the Shippable build service. They will begin running tests and doing builds based on some information I've put into the repository. Shippable, this adorable little II, will then drop that container off into ECR, where I have versioned artifacts of all the previous builds that I've done, and it will refer to the latest version and create a new task definition and create a service and attach it to an Elastic Load Balancer from this new container. So let's take a look and hope this works on my Wi-Fi. Should I upgrade to El Capitan right now? Probably not. I'll avoid that. Oh, I can't. This isn't good. I can't see this. Okay. Let's see if I can make this work from over here. Cool. So we have Chrome here. First thing we're going to do is we are going to, oh man, okay. Let's look at EC2 Container Service. I have a cluster running here that I spun up with CloudFormation earlier, hence the crazy name here. It has 3 container instances running in it, and it has 4 tasks running. Those 4 tasks are distributed across 2 different services, so that's important to note right now. What I would actually like to do first is go over to my terminal. Let's go ahead and clear this. Let's go over here. Let's go ahead and clear this. So I'm in my repository right now. Let's go ahead and make a change to the application. Man, this is really testing my vision. And so I'll do this like I did earlier. We'll change this comment for demo commit. All right, we'll just delete this. Great. Cool. So we can get -a. We can git commit -m, test commit. All right, and then we will git push. And it is relevant to note that I am using my master branch here because my master branch is what's configured to be watched in shippable. And so what's going to happen is a build is going to be kicked off here, and I just want to make sure that we have the possibility of having that finished before everything else is done being set up here. So I have my two services. I have my front-end hit counter application. Let's take a look at this. So we can see that it has 3 different tasks running. It's relevant to note here that the application is named hit counter. And then back on the cluster again, let's look at the other service that I have. We have this Redis service. And it's interesting to note that its name is Redis. So the hit counter application, I should have showed you this first. The hit counter application here very simple Python application with a little bit of CSS around it. The important thing to look at is this line here. So we are building the Redis connection string, and we are defining the host as just Redis, which, as you saw earlier, is the name of the container running in the service, running in the Redis service. So let's, real quick, look at the front-end application. See how it works. Pull up my load balancer in the EC2 console here. We'll grab this A record. So we've got this little application, as I mentioned, just a little hit counter. So how is it resolving Redis? Let's take a look at, on an instance here, how that works. So we can go to demo, nice little alias for my ECS instance. Quick Docker PS, so we can see what's running on this. Can everyone see that? Is that OK on the terminal? Cool. All right, that looks good. We have a few different Weave containers running. So we have the Weave proxy, we have the Weave net container running. We also have Weave scope, which we'll talk about in just a little bit. But we can see that we have both the back-end data container and the front-end application running on this particular instance. One thing we should do is let's tell Docker to use Weave in this session here. And then what we can do is we can run a dig command. So if this is confusing, we're running a dig command inside of a container. So it's going to be using Weave for service discovery underneath. We're looking up the hit counter application. This is just completely unqualified domain lookup. And it's going to return the results to the console here. So I hit enter. And we can see that we are given the 3 IP addresses of the nodes where the hit counter application lives, right? And so we can run it again. And we can see that we get the same subset of IP addresses, just in a slightly different order. Actually, it's in the same order this time because it's round robin. Let's get it to do a different set here. Cool, so it's in a different order this time. So that's interesting, right? So what else we can do is take a look at shippable here. And let's look at the application we're building with shippable. So another Python Flask application. We're doing much the same here. We're building the Redis connection string, which is on line 26 here. We're pointing out that the Redis host is just Redis. And we don't really care where this service drops into our cluster because we know it's going to be able to reach Redis by just its name because of Weave service discovery underneath. So let's see if shippable has kicked off a build yet. I think I have a build in progress here. And we can see a bunch of information, maybe. If you're in the back, I'm not so sure. So what's happening, right? So shippable's spinning up some nodes on the back end to actually do this build for me. It's pulling an image, some base images. It's booting a container. It's syncing my Git repository locally and building the container. And we can see that, let's see, where is this? So the post CI option here, where it's going to take that build and push it off to Elastic Container Registry, or EC2 Container Registry, rather. You could use Docker Hub as well here. So where is it getting this configuration information? If we look back in the GitHub repository for this application we're building with shippable, there's a couple of things, right? So it needs a Docker file, obviously. It needs to understand how to build that container, first of all. So we're saying we're starting with this default Python base image. and we're running a command inside of it, which is basically just gunicorn, just a standard WSGI web server for Flask. We're telling it what port to listen on. So that's important, but also important is requirements.txt. So this is something that Shippable will also pull in. This is used for when you're building a Python application, you have some pip packages you want to pull in. In the build, it will grab all of these things. And then finally, the most important part is the shippable.yml, which is, I hope you guys can see this. Here I am specifying to build containers, tag them a certain way, right? So tag them according to my ECR repository and then push them up to my ECR repository using this branch.buildNumber naming scheme, right? So we should see the latest build having the same branch name, so that should be master, and the build number should be the latest build according to how many builds I've done, right? So I think it was like 15 when we looked at Shippable last. So it has a push, great. Other interesting things here in Shippable, you also configure a pipeline, and this kind of tells you what's going on here. So our pipeline, we can configure the destination environment, so that is AWS ECS here. That's just what I've named it. We're pointing it towards the cluster that I had spun up earlier. Let's see, what else is important? If we look at this deployment configuration, we're also able to specify things like what port should it be listening on? Should it be using an elastic load balancer? So I've specified to hook it up to this elastic load balancer here that I spun up with my CloudFormation template earlier. And so if we go back to the ECS cluster, we should see a new service running. So let's look at the cluster. We have a third service running. And so let's take a look at this guy. We've got a load balancer over here for him. Spinning. Another A record to grab. And I might be jumping the gun a little bit on my ELB health check here. So for the sake of this, let's take a look at that service on the actual instance that is running it. Oh, it stopped. That's not good. That's the first time that has happened for me. Cool. All right, so I can show this in my backup video. We don't have to watch me fumble around with why did this stop, but why did it stop? What's our event here? I'm very curious. Unhealthy in ELB. Interesting. Maybe it came up too slowly. Okay, not a problem to troubleshoot here. We'll look at the backup video. Something else I wanted to point out is WeaveScope, which is one of my favorite things that Weave produces. Super cool. So what's happening here is they are giving you a representation of all the containers that are running on your cluster and also drawing relationships between these particular containers that are running. So for example, when this application stack first stands up, there are no lines drawn between any of these containers. And as they start interacting together, you get lines drawn, which is great. So it shows you what's happening. That was my other service down here that just disappeared because it didn't run successfully. But another great thing to do is click on one of these containers, and you can see all sorts of interesting information about them. So you can see what actual container is running. We can see how much memory usage it has, and we can also do cool things like get a shell on it right here. So we can drop in and check out the environment details of that particular container. So super helpful information with WeaveScope. You know what, let's go, because I feel like I have to show this working, let's grab my Summit demo video here. Wonder if I can pull this up on the other page. At the very end, we drop, so my deployment works as of an hour before this presentation. So we click on it. We go directly to the service. We can click on the link. We can bring up the new application, which is less pretty than the first one anyway, so no big deal, no major loss here. But we enter some sample values, and this application communicates with the Redis backend. So I'm saying enter these values into Redis, right? So great, and how can I prove that that actually worked? We can go back to WeaveScope here, and we can take a look at this container and watch it draw relationships between, we hit that from the internet, and we can see the Redis application has drawn a line to the sign-up application. So that's a quick summary. A little bit disappointed that it didn't work live, but that is why this video exists. And hopefully it communicates the idea of how that should work. I think I did a pretty good job of timing, and I think we have probably 15 minutes for Q&A and for a little bit of chatting. So as I mentioned before, myself, Devashish from Shippable, and we have Matt from Datadog will be up here hanging out, and we'd love to talk to you guys and answer your questions.